Welcome to lecture number 39 of the course on nonlinear structural analysis, theory and applications. So, let us recall what we have been doing over the last few lectures. Okay. So, in the last lecture, we have discussed extension of plasticity theory, okay, to study the PM interaction for steel cross sections, okay, and we have considered an idealized wide flange section, idealized meaning that each flange was represented by a single fiber, okay, and then there was no wave, the area of the wave was 0. So, we have basically got two steel fiber, okay, with elastic perfectly plastic material behavior, right. And we concluded that the plasticity theory works well for steel cross sections. Okay. In this lecture, we will see how we can extend this or find ways to model PMM. PMM means axial force, moment about one axis, let us say the major axis, and moment about the other axis, the minor axis bending, okay, for realistic steel as well as reinforced concrete cross sections. Okay. Note that the stress resultant plasticity models that we have been discussing with associated flow rule are generally used to model concentrated plastic hinge behavior in beam column elements. Okay. What is concentrated plasticity model? What is the other one, distributed plasticity? Well, that is the next topic of the next lecture. Okay. So, we shall discuss soon. Also note that OpenSys does not have stress resultant plasticity models. So, therefore, I will not be able to show you any example problems. Nevertheless, there are other computer programs, for example, the CSI software, for example, SAP 2000 or ETABS, this software actually have this feature. Okay. So, let us see how we can model this PMM interaction using the stress resultant plasticity in this kind of computer programs. Again, I will not do an example, but we will talk about the theory. So, this is the example that we did in the last lecture. We have one fiber here representing a flange, and this is another fiber representing the other flange. The area I took A by 2 and A by 2. So, what we did, we applied first some axial load. So, we went to point 1 and then applied moment. So, we went to point 2, okay, on the yield surface, and then we increased the curvature. So, we remained on the yield surface for reasons that I explained in the last lecture, that the normal to the yield surface is along this direction, and all the curvature that we imposed between 2 and 3 is the plastic curvature. Okay. And if you look at the plastic axial strain and the plastic curvature, this is actually in the direction to the normal to the yield surface. Okay. So, therefore, the point remains here, and then we cycled it and moved in this direction, came to this point, okay, and stayed there. So, the resulting moment versus curvature relationship was like this, right. And in the force versus axial deformation, that means the axial strain measured at the reference axis, okay, is something like this. And what you see, that when I apply this cyclic bending, then from point 0 to 6, there is an accumulation of plastic deformation, and which in this case is axial shortening. Okay. So, we are in this direction, and this is my compression axis. So, the deformation, axial deformation is also compression, and it accumulates. So, let us keep that in mind. Okay. And we also made this conclusion that if you cycle many times, the axial deformation can be substantial. Okay. So, we concluded that plasticity theory can correctly account for the PM interaction in steel sections. Analysis of more complex cross sections show that the plasticity theory can make reasonably accurate predictions of steel cross section behavior. Okay. So, this statement is coming out of the CSI technical note, okay, and I am sure they might have studied it, right. Then the CSI software uses a PMM yield surface, which I was talking about, which is similar to that described in this paper. Now, in the interest of time, I will not be getting into the approach that was taken or developed in this paper. So, they have used a bounding surface plasticity approach, where they have initial yield surface and a bounding surface, and then they are using the kinematic hardening. So, we will not get into those discussion, Okay. But I want to show you what the CSI software, for example, SAP 2000 or ETAB basically does. Okay. So, it defines a PMM yield surface, which in the first quadrant looks something like this. So, let us say you have, this is your axial force, this is the moment about y axis, this is the moment about z axis. I am still talking about steel cross section. So, let us say if I draw an I section or wide flange section. So, this looks something like this. Okay. So, this is referring to this figure, this is my z axis and this is my y axis. So, y is the minor axis and z is the major axis, and in the SAP notation this is 3 and this is 2. So, they call it M2 M3, okay, as you can see PM2 or PM3, right. Now, this is a surface, as you can see in the first quadrant you have the surface, and similarly you have in the other quadrant. If you go back to the previous lecture, you will see the complete surface, right. Now, how it is defined in this computer program, for example, the CSI program. So, they define the PM yield surface. So, that means PM means you consider this versus that by taking my is equal to 0. So, that means this is the surface, okay, or you consider this moment to be 0, then you are looking at P versus my, which is this one, right. So, it is a projection on one of the PM plane, okay. So, either PM2 plane, PM2 means PMY plane, or PM3 plane, that is PMZ plane. Okay. Then the yield function is P by Py0. What is Py0? Is the yield force, and M by My0, My0 is the yield moment. Okay. And then there is this exponent alpha for this axial force ratio and exponent beta for the moment ratio. Minus 1 is equal to 0. This is my yield function. Okay. And as an user, you can give different values of alpha and Py0 for tension and compression. So, let us say this is my compression and this is the moment and this is the tension. So, basically I am plotting axial force versus moment. Okay. This could be mz or my. Now, for tension and compression, you can give different values of Py. So, that is Py0, which is shown as Pyc or Pyt for compression and tension respectively. Okay. And you can also give different values of alpha for the PM2 and PM3 planes. Okay. So, that means for this plane, that means PMZ or PMY, you can give different values of alpha. So, this defines on one plane what is the curved line. Okay. And then to get the surface, you need this equation, the interaction, or in other words My Mz interaction, or here it is M2 and M3 interaction. Okay. How it is done? So, the yield function in the M2 M3 plane, that means if you take a plane and cut this PM yield surface, okay, then let us say this is the axial force. So, then you get basically a curve like that. Okay. So, that is defined by this equation. Now, what is M2? Well, M2 is the bending moment. Let me write it here. So, this is M2 and this is your M3. Okay. So, this is the moment, applied moment, and then M2yp and M3yp are basically coming from equation 1, which I shall show. Okay. So, let me go back to this. So, at this value of axial force, I go back to the previous equation and substitute here, right, and then I solve for this M. If it is for 2 axis bending or y axis bending, then whatever value of M I get, that I will call M2yp. Okay. Similarly, M3yp. Okay. So, these values will go in here and here. So, all I am doing is for a given axial force, I am trying to define this, okay, where this number, if you drop down vertically, this point is your M2yp and this point is your M3yp. Okay. So, now these two equations together define this complete surface in 3D. Okay. So, this is what I stated here, and gamma is a parameter that is defined by the user to model this interaction. Okay. Now, the force deformation behavior for moment as well as axial force. If I am plotting the axial force versus axial deformation or bending moment versus the corresponding deformation, which is the rotation, is given by this behavior. Okay. Now, what are these points? Well, initially the behavior is rigid. So, that means it will go like this and then it will yield at point B, okay, which the program automatically calculates, and then the yield, which is point B, ultimate, this one, I mean you can modify this, that is the reason I am writing yield point, okay, the ultimate, then this point, the residual strength can be independently specified. This is horizontal, okay, which is default. So, now if you specify this point force is equal to that, then you would be getting kind of an EPP behavior like that. Okay. So, you define these points for compression. Compression means you have axial compression and assume that M2, M3 are 0. So, basically what you are doing, you are defining the force deformation response for each component. Okay, you are defining for axial force versus axial deformation, bending moment versus rotation. So, for compression you can define this point. If they are not the same for tension, then you define again for tension with M2, M3 equal to 0, and then you define it for bending moment about 2 axis, that is M2 taking M3 and P is equal to 0, and bending moment about 3 axis taking M2 and P is equal to 0. So, these are the input that goes into the program, and then the program uses the method that I told you the reference, okay, and accordingly using the plasticity theory determines the PM interaction. Okay. I mean the PM interaction curve is given, but actually determines the response for any given deformation vector. What is our deformation vector for the cross section level? If you recall, we denoted by V bar, which is our epsilon and psi. Okay. So, for more details you can go to the CSI reference manual and see the details. I am not doing examples because many of you may not have access to this proprietary software, hence I will not do any example, but you can get in touch with me if you would like to discuss anything in particular. Okay. So, now for RC section, let us see what happens. Does plasticity theory work? Okay. So, RC section is complicated. So, what I will do, I will take a very similar example, okay, like we did earlier for steel cross section, and this is coming out of this book by Professor Powell. Okay. So, here I have a concrete fiber, a single fiber, and then there is a single steel fiber. Okay. And then here also I have another concrete fiber and a single steel fiber. This is the simplest form of a column that we can imagine. It is not a real column, but we are trying to idealize it. Okay. So, the column looks something like this, and also we are assuming for steel the behavior is something like this. So, if I draw sigma s for steel and epsilon s for steel, so the behavior is elastic, perfectly plastic in tension as well as in compression. So, this is sigma ys negative and this is sigma ys positive, right. So, that is for steel. So, let us say this is my tension and this is my compression. Okay. Remember, for PM interaction we always plot the compression above. Now, for concrete it is like this. So, for concrete it is assumed that just for this demonstration, for this example, okay, it is like this. So, you have elastic perfectly plastic behavior in compression and no tensile strength capacity for concrete. So, this is 0. Okay. So, this is our assumption for the steel and concrete behavior, right. Now, the interaction surface, the PM interaction becomes something like this. Okay. It is something like this. Now, let me try to explain to you the salient points, these points. Okay. So, first let us consider this compression strength. Okay. How do I calculate this compression strength? Well, the stress distribution corresponding to compression strength is like this. If I draw, so here I am drawing. Okay. So, this is compression and this is compression. How much can this be? Well, let us say the steel is completely yielding and concrete has reached its strength of sigma yc. So, this is going to be AS, the area of steel fiber, multiplied by sigma ys, okay, and plus AC multiplied by sigma YC, and the same is here, AS sigma YS plus AC sigma YC. Okay. So, if you add the two together, that is our axial compressive strength, which is 2 AC sigma YC plus 2 AS sigma YS. This point is done, right. For the tension, okay, this point we know when it is under tension, the concrete strength is 0, right. So, then this becomes, let me reverse the direction. So, for tension it is like this, only steel is carrying. So, sigma YS into AS, and this is sigma YS into AS, that is the strength, because concrete is carrying no tension. Okay. So, if you add the two together, the axial tensile strength is 2 AS sigma YS, very easy to understand. Okay. Now, let us come to this point, which is called the balanced point, right. We have also discussed earlier what is the balanced point. Now, I want to calculate what is the force and what is the corresponding moment at the balanced point. Okay. So, to do that, let us first see what is the stress distribution. So, we are assuming the direction of bending moment is like that, right. So, if that is the direction, I will say that the concrete, so this is compressive, okay, concrete reaches its strength. So, AC sigma YC plus the steel has reached its yield strength AS sigma YS. Okay. On the tension side, the steel has yielded, but the concrete has cracked. So, it cannot take anything. So, it is simply AS sigma YS. Okay. So, if this is the case, then what is the resultant force? Well, the resultant force is sum of the two. So, this is, I will show, this is the resultant, this is P, and this is the resultant moment M. So, how do I calculate P? Well, P is equal to AC sigma YC plus AS sigma YS minus AS sigma YS, which is going to give me AC sigma YC. Okay. So, this is what is written here. Okay. Now, for the moment, so this is the resultant moment that we are trying to calculate. So, if I take moment about the reference axis, about this axis, then what do I get? Bending moment M is equal to AC sigma YC plus AS sigma YS into d by 2, okay, plus AS sigma YS into d by 2. Okay. So, this gives me 0.5 AC d sigma YC plus this will get added AS sigma YS multiplied by d. Okay. This is exactly what is written here. Okay. So, this is the balance point moment. So, we know this value, we know that value. So, we have established this, this and this point, and because we are talking about single fiber, the variation is linear. Okay. If you have multiple fiber, okay, then you will get the actual curve, which is something like that. Okay. And we call that point is the balance point, right. Now, using a very simple example, using this example and a load value which is below the balance point, let us say I am applying a load like this. Let us do this little bit. I am applying axial force up to this and then applying the bending moment. So, I come to this point, right, like so. I come to this point, right. So, what kind of plastic deformation I have? So, what is the normal to the yield surface? According to the plasticity theory, I am using associated flow rule. So, this is the direction of my plastic deformation vector. So, what is the plastic axial strain? Is it tensile or compressive? Remember, this is my compression positive and the plastic axial strain is going in the opposite direction. So, that means I will have axial extension, right. So, when I go from here to here in the concrete column at the reference axis, according to the plasticity theory, I get axial extension. And if you recall the previous example where the yield surface was like this, we went this way and we got cumulative axial shortening. So, in this case what happens? We go like that. Now, if I cycle like so, right, then what will happen? The concrete column will extend according to the plasticity theory. So, this growth is not very accurate. Okay? That is where plasticity theory fails to predict the behavior of a reinforced concrete section. Okay? So, that is what Professor Powell writes in his book, that plasticity theory does a mediocre job of modeling PM interaction in RC section for monotonically increasing load and a poor job for cyclic load. The major problem, like I mentioned, for P below the balance point, the plasticity theory incorrectly predicts progressively increasing axial tensile strength. That means your column is growing in length when the load is small below the balance point, okay, when bending deformation is cycle. So, this is the problem with the plasticity theory applied to reinforced concrete section. Does that mean that the plasticity theory is not useful for RC section? Well, it is useful. Okay. Plasticity theory is useful for practical modeling of reinforced concrete columns. As we move forward, you will see that every model has its own limitation. Okay. So, and if you go back and recall the first probably towards the beginning of the course, I said all models are wrong and some are useful. Similarly, we know that this has severe limitation, but still if you do not worry too much about the axial deformation, or if the axial deformation is not going to affect your final result that you want, then you can go ahead and use the stress resultant plasticity theory for the reinforced concrete column also. So, therefore, CSI software also has parametric PM2 M3 hinge for reinforced concrete members as well. Okay. So, with that, let us recall one single thing that we want to discuss further. We have so far discussed associated flow rule. Okay. Associated flow rule means your plastic strain increment for von Mises yield surface is normal to the yield surface, or for stress resultant plasticity, we said the plastic deformation vector is along the normal to the yield surface, that is our PM yield surface, right. We have not talked about non-associated flow. So, before I finish this topic, I thought of giving you an example of non-associated flow. So, let us consider a bearing pad. Okay. Let us say I have a bearing pad like this, right, and it is subjected to a vertical force P and a horizontal shear V, and this is sitting on a surface. Let us assume the friction coefficient is mu and it is constant. Okay. This constant mu can be questionable, but still let us assume that the friction coefficient is constant. Okay. So, how does the PV interaction look like? Okay. So, this is my axial force and this is the shear force V, right. So, we know that the shear force required to cause a slip V is equal to mu into this force P, as simple as that. So, V is equal to mu into P. So, if I plot this, it is a straight line. So, this is mu and this is unity. Okay. Now, if you consider in 3D, this V can be in any direction. So, then what you get? You basically get a cone. Okay. So, then this becomes a cone like that, where V is, you can take in two mutually perpendicular direction. Let us say we are talking about this simple 2D. Okay. So, now let us say I am applying some axial force, just like earlier we are applying axial force in a column and then applying the bending moment. Now, I am doing the similar thing. I am applying the axial force going along this path, and I have applied so much of axial force P, or the vertical load P, right. Now, I am trying to increase this V. Okay. So, I am moving along this path and I come to this point. So, when I come to this point, what should happen? Well, the bearing pad will slip, right, because it has reached the yield surface. So, this is the slip surface, or also called the yield surface. I reach that, V is equal to mu into P. So, it is in the verge of slipping. Okay. What is the direction of the slip? Well, we can see from here the direction of the slip is horizontal, isn't it? So, it is in the direction of V, right. But if we use associated flow rule, this is my yield surface, then what should be the direction of the slip? If we use associated flow rule, it is going to be in this direction. So, that is neither in V nor in P, right. But as we know, in this case the slip is in the horizontal direction. So, here the flow, that is the slip, is not associated with the yield surface. Okay. So, hence we call it a non-associated flow for this kind of conical yield surface. Okay? And in soil, you have this kind of yield surfaces, okay, whether it's Drucker-Prager or Mohr-Coulomb, and there you cannot use associated flow rule, you have to go for non-associated flow, okay, or non-associated flow rule. And as you can see, this is a simple example of non-associated flow. So, with that, let us recall what we have done in this lecture. We have discussed the application of plasticity theory to PMM interaction, that means PMY-MZ or PM2-M3 interaction, and we have also talked about its limitation, that plasticity theory assume that the normal is normal to the yield surface is the direction of the plastic deformation factor, which may not be always true, and hence the plasticity theory is not very accurate, but it works for steel cross sections. For reinforced concrete cross section, it fails because it cannot consider the cracking of concrete and crack closing. That is not coming into picture. We just have the yield surface and we are working with the yield surface. Hence, the cracking is not coming into picture. So, therefore, it has some limitations. Nevertheless, plasticity theory can also be useful for reinforced concrete sections. Okay? And we have also talked about an example of non-associated flow for friction. Okay? So, in the next lecture, we will be talking about the concentrated versus distributed plasticity models or approaches to model lateral load resisting systems for earthquake loads. Okay? So, these are the references that I have used. Please go ahead and read if you are interested. So, this RC section you can find from this book, and this is the approach that CSI software uses for the parametric PMM hinge. Okay? With that, thank you and see you in the next lecture.